Did you know that right now, as you sit quietly, you are spinning at nearly 1,000 miles per hour? You don't feel it because Earth moves slowly, smoothly, in perfect balance. But the truth is, your home, your street, your city, all of it is a rotating piece of rock drifting through space. The continents are shifting, the oceans are carrying energy through their depths, mountains are rising in silence, and beneath your feet, a vast ocean of molten metal is flowing in darkness, shielding you from the quiet storms of space. The air you're breathing once existed when dinosaurs walked this planet. The water flowing through your veins may have once been part of an ancient sea. Earth does not make noise. It simply keeps changing, so slowly that it feels still. And tonight, we are going to feel that slow motion together. 100 calm, fascinating, and deeply relaxing facts to remind you that you don't just live on this planet, you are traveling with it. If these peaceful journeys bring you comfort, don't let this one end here. Gently tap the like button so YouTube knows that more people need moments like this. Subscribe so the next time we set out on a quiet scientific adventure, you'll be right here with us. And leave a small comment below. Tell me, which part of Earth feels the most mysterious to you? Now, slow your breathing. Let your shoulders relax and allow yourself to drift into a story that has been unfolding for billions of years and is still continuing tonight. Let's begin. Right now, as you rest, Earth is moving in ways too slow and too vast to feel. The planet beneath you is not fixed or silent. It is part of a long, unfolding story that began more than 4.5 billion years ago when dust and rock circled a young sun. In the beginning, there was no solid ground. There was heat, motion, and collision. Tiny grains of cosmic material clung together, forming larger and larger bodies. Gravity pulled them inward. Impacts released enormous energy. Early Earth was molten, its surface glowing, its interior churning. As time passed, the heaviest elements sank toward the center. Iron and nickel gathered deep below, forming a dense core. Lighter materials floated upward, cooling gradually to form a crust. This separation created layers, like a planet-sized sphere quietly organizing itself from the inside out. The surface did not cool instantly. Volcanoes released gases. Steam rose from fissures. Over millions of years, water vapor condensed and fell as rain. That rain may have lasted for centuries, filling basins and creating the first oceans. Lightning flashed above dark waters. Tides moved under the pull of a young moon. Beneath the surface, heat continued to move slowly upward. Convection currents stirred the mantle, carrying warmth from the deep interior toward the crust. These slow motions eventually fractured the outer shell into large plates, and those plates began to drift. Continents were not always where they are now. Over immense spans of time, land masses gathered into supercontinents and later broke apart again. Oceans opened and closed, mountains rose where plates collided and were worn down by wind and rain. The map of Earth has been redrawn many times. While stone was shifting, something else was happening in the seas. Chemistry grew more complex. Simple molecules assembled into structures capable of copying themselves. Life began quietly, likely in water warmed by volcanic heat or lit by sunlight filtering from above. For billions of years, life remained microscopic. Tiny organisms changed the chemistry of the atmosphere, slowly adding oxygen. That oxygen transformed the planet, allowing more complex forms to evolve. Forests appeared, insects buzzed, reptiles walked, mammals emerged, and eventually humans looked up and began to ask questions. Through it all, Earth kept moving. Its magnetic field formed as liquid iron circulated in the outer core, creating a protective shield against solar radiation. Its atmosphere thickened and shifted. Ice ages came and went. Sea levels rose and fell. Meteorites struck and left scars that softened with time. The ground beneath you holds memories of all of it. In layered rock, in fossil shells, in mineral crystals aligned with ancient magnetic fields, Earth has recorded its own biography. And tonight, as you listen, you are part of that story too. Because the planet is still cooling, still shifting, still changing, and the slow rhythm of that motion continues beneath your feet. As Earth continued to cool, its surface became a place of contrast. Solid crust floated above a restless interior. Oceans collected in low basins, while early continents formed from lighter, buoyant rock that resisted sinking back into the mantle. These first landmasses were small compared to today's continents, but they marked the beginning of stable ground. Stability, however, is relative on a planet driven by heat. Beneath the crust, convection currents moved slowly but persistently. Hot material rose from deeper layers, spread outward, cooled, and sank again. This circulation placed stress on the surface. Over time, the crust fractured into massive plates that began drifting atop the softer mantle below. Where plates moved apart, new crust formed. Magma rose through cracks, cooled and solidified into fresh ocean floor. Long underwater mountain chains stretched across the planet, unseen beneath the waves. These mid-ocean ridges quietly built new seafloor in darkness. Where plates moved toward each other, sometimes slid beneath the other. This process, called subduction, carried oceanic crust down into the mantle. There, heat and pressure transformed it. Some melted and rose again as magma, feeding volcanoes that lined certain coastlines. And where continents collided, neither easily sank. Instead, the crust crumpled and thickened. Rock layers folded and uplifted. Mountains rose slowly, not in a single violent motion, but through millions of years of compression. Even today, some mountain ranges continue to grow by mere millimeters each year. While stone shifted, oceans circulated. Wind patterns, shaped by Earth's rotation and uneven heating from the sun, drove surface currents. Cold, dense water near the poles sank and flowed along the ocean floor, while warmer water moved toward higher latitudes. This global conveyor of water distributed heat around the planet, moderating climate. The moon played its part as well. Its gravity pulled on Earth's oceans, creating tides. These daily rises and falls stirred coastal waters, mixed nutrients, and may have influenced early ecosystems. The moon also helped stabilize Earth's axial tilt, preventing extreme swings in climate over long periods. Above, the atmosphere evolved. Volcanic gases once dominated the air, but over time, oxygen produced by photosynthetic organisms accumulated. This shift allowed ozone to form high in the atmosphere, creating a protective layer that absorbed harmful ultraviolet radiation. Life was then able to expand onto land. Rain fell. Rivers formed.
Water carved channels into rock, carried sediment to the sea, and reshaped landscapes grain by grain. Weathering broke down mountains, erosion transported their remains, deposition created new plains and deltas. The rock cycle turned continuously, transforming material from one form into another. Even the magnetic field continued its quiet work. Generated by motion in the outer core, it extended far into space, deflecting much of the solar wind. Without it, the atmosphere might have slowly thinned under constant particle bombardment. Through all these interconnected systems, Earth demonstrated something remarkable. It was not a static sphere of rock. It was, and still is, a dynamic planet where interior heat, surface water, atmospheric chemistry, and gravitational forces interact in an intricate balance. And that balance continues tonight, beneath the calm surface you see.
Over vast stretches of time, the continents did not simply drift at random. They followed patterns guided by the slow choreography of plate tectonics. Supercontinents formed when most of Earth's land gathered together, only to fragment again millions of years later. One of the most famous was Pangaea. Around 300 million years ago, nearly all major landmasses were joined into a single immense continent. Deserts stretched across its interior. Vast forests lined its edges. Reptiles wandered freely across regions that are now separated by oceans. But Pangaea did not last. Deep beneath it, mantle convection continued. Heat rising from the interior weakened sections of the crust. Cracks formed. Magma pushed upward. Gradually, the supercontinent began to split. New oceans opened as seafloor spread between separating land masses. What is now the Atlantic Ocean began as a narrow rift that slowly widened. The separation of continents changed climate patterns. As land shifted, ocean currents adjusted. Mountain ranges formed and altered wind circulation. Regions that were once humid became dry. Others that were arid became lush. Earth's surface and atmosphere responded together, constantly influencing one another. While continents moved, life continued to adapt. Mass extinctions punctuated the fossil record. At several points in history, dramatic events reshaped ecosystems worldwide. Massive volcanic eruptions released gases that altered climate. Asteroid impacts darkened skies and disrupted food chains. Yet after each disruption, life returned in new forms. Forests grew again. Oceans filled with diverse creatures. Mammals eventually rose to prominence after the extinction of the dinosaurs. The surface of Earth became a tapestry of interconnected ecosystems shaped by geology and time. Glaciers also left their mark. During ice ages, enormous sheets of ice spread across continents. Sea levels dropped as water became locked in frozen form. Landscapes were scraped and carved beneath the weight of moving ice. When temperatures warmed, glaciers retreated, leaving behind valleys, lakes, and scattered boulders carried far from their origins. Even deserts record change. Regions that are dry today were once covered by shallow seas or crossed by rivers. Sand dunes migrate slowly under persistent winds. Layers of sediment preserve evidence of climates long gone. The Sahara, for example, has alternated between green landscapes and arid expanses many times.
Throughout all of this, the sun remained a steady influence. Its energy drives atmospheric circulation, ocean currents, and the water cycle. Subtle variations in Earth's orbit and tilt influence long-term climate cycles. These orbital shifts, unfolding over tens of thousands of years, contribute to the pacing of ice ages. Beneath everything, the core continues to flow. Liquid iron moves in slow currents, generating the magnetic field that shields the planet. Occasionally, the magnetic poles reverse, switching places over thousands of years. These reversals are recorded in cooling lava and ocean crust, like silent signatures of change. Earth's history is not a straight line. It is a rhythm of gathering and dispersing, warming and cooling, building and eroding. Every rock layer, fossil bed, and coastline carries part of that rhythm. And as you rest tonight, that rhythm continues. Continents still drift, oceans still circulate, mountains still rise and fall. The planet beneath you remains in motion, steady and patient, writing its story one quiet change at a time.
If you could watch Earth from far above for millions of years, the oceans would appear alive with motion, not chaotic, but rhythmic. Currents trace invisible highways across the globe, redistributing heat, nutrients, and energy in patterns that shape climate and life. At the surface, winds push water into broad gyres. In the northern hemisphere, these currents curve clockwise. In the southern hemisphere, they turn the opposite way. This circular motion is influenced by Earth's rotation, which subtly deflects moving air and water through what is known as the Coriolis effect. It is a gentle force, but over vast distances, it organizes entire oceans. Warm water flows from equatorial regions toward higher latitudes. As it travels, it releases heat into the atmosphere, moderating temperatures in places far from the tropics. Regions that might otherwise be much colder remain temperate because of these steady marine currents. But surface motion is only part of the story. Below, a slower and even more powerful circulation unfolds. Cold, dense water forms near the poles where temperatures are low. In some regions, sea ice forms and leaves salt behind in surrounding water, making it heavier. This dense water sinks toward the ocean floor and begins a slow journey across the globe. This deep current moves quietly, often taking centuries to complete its path. Eventually, it rises again in distant regions, bringing nutrients from the deep ocean back toward the surface. This global conveyor belt links distant seas into one interconnected system. Tides add another layer of motion. Driven primarily by the gravitational pull of the moon, tides raise and lower ocean levels twice each day along many coastlines. These movements stir coastal waters, influence marine ecosystems, and shape shorelines over time. Though the rise and fall may seem modest, their persistence reshapes land grain by grain. Storms can temporarily intensify ocean motion. Hurricanes draw energy from warm surface water, transferring heat into the atmosphere. Powerful waves rearrange beaches and barrier islands. Yet even these dramatic events are part of larger planetary cycles, redistributing energy rather than creating it. The ocean also absorbs a significant portion of the sun's heat. Because water warms and cools more slowly than land, it acts as a stabilizing force in Earth's climate system. Coastal regions often experience milder seasonal changes than inland areas, buffered by the nearby sea. Beneath the waves, life depends on these motions.
Upwelling zones, where deep, nutrient-rich water rises, support abundant marine ecosystems. Phytoplankton flourish in these regions, forming the base of ocean food webs. In turn, fish, seabirds, and larger predators gather where currents bring nourishment. Even the chemistry of the atmosphere is linked to the sea. Oceans exchange gases with the air, absorbing carbon dioxide and releasing oxygen produced by marine organisms. This exchange influences global climate and supports life far beyond the shoreline. Though the ocean may appear calm tonight, it is never still. Currents are flowing, heat is moving, tides are rising and falling, and across vast blue expanses, Earth continues its slow, balanced circulation, steady and enduring.
Beneath the calm surface of the oceans lie some of the most dramatic landscapes on Earth. Far from sunlight, the seafloor stretches in ridges, plains, and trenches shaped by the same tectonic forces that move the continents. Along mid-ocean ridges, new crust is constantly being created. These underwater mountain chains form where plates pull apart. Magma rises through fractures, cools quickly in contact with seawater, and hardens into basalt. Layer by layer, fresh seafloor spreads outward from the ridge crest, carrying a magnetic signature of the planet's field at the time it formed. This process is slow but continuous. The ocean floor you would stand on today may be far younger than the rocks beneath a continent. Most oceanic crust is less than 200 million years old, recycled through subduction long before it can become ancient. In other regions, plates converge. When dense oceanic crust meets lighter continental crust, it sinks beneath it, descending into the mantle. This creates deep ocean trenches, some reaching more than 6 miles below the surface. Above these zones, chains of volcanoes often form as melting rock rises again toward the surface. The deepest trenches are places of immense pressure. Water above exerts crushing force, yet life exists even there. Specialized organisms thrive in darkness, feeding on chemical energy rather than sunlight. These ecosystems demonstrate how adaptable life can be when given even the smallest opportunity. Hydrothermal vents are among the most remarkable features of the deep sea. Here, seawater seeps into cracks in the crust, is heated by magma below, and rises back to the seafloor, rich with dissolved minerals. The hot fluid creates chimneys of mineral deposits and supports entire communities of organisms that rely on chemical reactions for energy. These vent systems reveal that life does not depend solely on sunlight. Chemical gradients can sustain ecosystems independent of surface conditions. Some scientists believe similar environments may have played a role in the earliest stages of life on Earth. Sediment also blankets much of the ocean floor. Tiny shells of plankton, fragments of rock carried by rivers, and dust blown from distant deserts slowly settle into layers. Over time, these sediments compress and harden into stone, preserving microscopic fossils and chemical traces of past climates. Submarine landslides occasionally reshape the seabed. Triggered by earthquakes or rapid sediment accumulation, these events can send massive amounts of material downslope. Though hidden beneath water, they leave scars and deposits that tell of sudden change. The ocean floor is not smooth or featureless.
It contains vast volcanic plateaus, fracture zones that offset ridges, and underwater mountains called seamounts. Many of these features remain largely unexplored, mapped only by sonar and remote vehicles. Despite its remoteness, the ocean floor influences the entire planet. It regulates carbon storage, shapes ocean circulation, and drives tectonic recycling. Its processes are slow, but they operate continuously. Tonight, while you rest above the surface, new crust may be forming in darkness. Old crust may be descending into the mantle. And in the silent depths, Earth continues rebuilding itself, unseen but never inactive.
While tectonic forces reshape the crust from below, water reshapes it from above. Rainfall, rivers, and glaciers act as patient sculptors, transforming even the hardest rock through persistence rather than power. Weathering begins the process. Rock exposed at the surface encounters wind, water, temperature changes, and chemical reactions. Some weathering is mechanical. Water seeps into cracks, freezes and expands, slowly widening fractures. Roots grow into tiny openings and apply pressure as they thicken. Over time, solid rock breaks apart into smaller fragments. Other weathering is chemical. Rainwater absorbs carbon dioxide from the atmosphere, forming a weak acid. This slightly acidic water reacts with certain minerals, dissolving them gradually. Limestone landscapes are especially vulnerable, developing caves, sinkholes, and underground rivers carved by subtle chemical change. Once rock fragments loosen, erosion moves them. Rivers carry sediment downhill, sorting particles by size and weight. Coarse gravel settles quickly, while fine clay may travel long distances before being deposited. As rivers meander across plains, they carve outer banks and deposit sediment along inner curves, constantly shifting their own paths. Over time, valleys deepen. A young river often cuts sharply into bedrock, forming steep-sided valleys. As the landscape matures, slopes soften and widen. Floodplains develop where rivers overflow during heavy rainfall, leaving behind fertile layers of sediment. Deltas form where rivers meet the sea. As flowing water slows upon entering an ocean or lake, it drops its sediment load. Layer by layer, new land extends outward. These regions are dynamic and productive, but also vulnerable to rising sea levels and changes in sediment supply. Glaciers reshape land differently. Instead of flowing water, they use massive weight and slow movement. As ice advances, it scrapes bedrock, smoothing some surfaces and carving others into deep valleys. When glaciers retreat, they leave behind ridges of debris, scattered boulders, and basins that may later fill with water. Wind also plays a quiet role. In dry regions, it lifts and transports fine particles, shaping dunes that migrate slowly across deserts. In colder climates, wind can sculpt snow into ridges and patterns that reflect subtle atmospheric shifts. Even coastlines are temporary. Waves erode cliffs, redistribute sand, and form barrier islands. Over decades and centuries, shorelines advance and retreat. What seems permanent during a human lifetime is fluid over geological time. All these processes are part of the rock cycle. Sediment deposited today may eventually be buried, compressed into stone, uplifted, and exposed again. Heat and pressure may transform it into metamorphic rock. If buried deeper still, it could melt and re-emerge through volcanic activity. Earth's surface is never finished. It is continuously being worn down and rebuilt, grain by grain.
Mountains rise through tectonic forces, only to be carved by erosion. Sediment travels from peak to plain to sea, only to return through uplift and subduction. Tonight, as you rest, rivers continue their steady flow. Rain continues to fall somewhere. Wind continues to move sand across quiet deserts. And through these gentle forces, Earth's landscape keeps evolving, patient and unhurried.
Above the shifting land and restless oceans lies a thin, protective layer that makes life possible. Earth's atmosphere may seem vast when you look at the sky, but compared to the size of the planet, it is remarkably delicate. The atmosphere formed gradually. Early volcanic eruptions released gases trapped within Earth's interior: water vapor, carbon dioxide, nitrogen, and other gases accumulated around the planet. Over time, as the surface cooled, water condensed and fell as rain, forming oceans and leaving nitrogen as the dominant atmospheric gas. Oxygen came later. For billions of years, Earth's air contained very little free oxygen. Then microscopic organisms in the oceans began using sunlight to convert carbon dioxide and water into energy, releasing oxygen as a byproduct. Slowly, oxygen levels rose. This shift transformed the chemistry of the planet and allowed more complex life to develop. High above, a special layer formed. Ozone, created from oxygen molecules, gathered in the upper atmosphere. This ozone layer absorbs much of the sun's harmful ultraviolet radiation. Without it, life on land would be far more difficult. It acts as a quiet shield, invisible yet essential. The atmosphere is not uniform, it is layered. The lowest layer, the troposphere, is where weather happens. Clouds form here, rain falls, winds move across the surface. Above it lies the stratosphere, where the ozone layer resides. Higher still are layers where temperatures shift dramatically and where the boundary between air and space becomes gradually indistinct. Air is always moving. Warm air near the equator rises and moves toward the poles. Cooler air sinks and returns toward lower latitudes. This circulation, combined with Earth's rotation, creates large wind belts that influence climate zones across the globe. Storms develop where air masses meet. When warm, moist air rises and cools, clouds form. Under certain conditions, powerful systems can emerge. Yet even the most dramatic storm is part of a broader energy balance, redistributing heat rather than creating it. The atmosphere also connects closely with the ocean. Evaporation transfers water vapor into the air. Winds drive surface currents. Heat exchanges continuously between sea and sky. Together, they regulate global temperatures and influence seasonal patterns. Tiny particles float within the air as well. Dust from deserts, ash from volcanic eruptions, sea salt from breaking waves, all become part of the atmospheric system. Some particles reflect sunlight, slightly cooling the surface. Others absorb heat. These subtle interactions shape climate over time. Even sound travels through this thin layer. The rustle of leaves, the rhythm of waves, the whisper of wind, all depend on air molecules vibrating and carrying energy outward. Without the atmosphere, Earth would be silent. Despite its importance, the atmosphere remains fragile. It is held close by gravity, but it can be influenced by changes at the surface and in space. Solar storms can disturb upper layers. Large volcanic eruptions can temporarily cool the climate by injecting reflective particles high above. Yet through all fluctuations, the atmosphere persists. Tonight, winds are circulating. Clouds are forming somewhere over distant land. Rain is falling into unseen forests. And above you,
This invisible envelope continues its quiet work, wrapping the planet in a thin layer of moving air that sustains every breath you take.
Beyond the atmosphere lies a boundary where Earth meets space. Though invisible, this region plays a vital role in protecting the planet from the constant stream of particles flowing outward from the Sun. The Sun does more than provide light and warmth. It continuously emits charged particles known as the solar wind. These particles travel across the solar system, carrying energy and magnetic fields with them. When they approach Earth, they encounter something remarkable. Deep within the planet, liquid iron moves in slow currents. This motion generates Earth's magnetic field. The field extends far into space, forming a protective bubble called the magnetosphere. Instead of striking the atmosphere directly, much of the solar wind is deflected around this magnetic shield. The magnetosphere is not rigid. It shifts and responds to changes in solar activity. On the side facing the Sun, it compresses slightly under pressure. On the opposite side, it stretches into a long magnetic tail that trails behind Earth like a quiet wake. Sometimes, the Sun releases stronger bursts of energy. Solar flares and coronal mass ejections can send waves of charged particles toward Earth. When these interact with the magnetosphere, energy is transferred into the upper atmosphere. This is when auroras appear. Charged particles travel along magnetic field lines toward the polar regions. As they collide with gases in the upper atmosphere, those gases emit light. Oxygen can glow green or red. Nitrogen can shimmer in shades of blue or purple. Curtains of light ripple gently across the sky, silent and luminous. Though beautiful, these events are also scientific signals. They reveal how closely connected Earth is to its star. Variations in solar activity can influence satellites, communication systems, and power grids. The magnetic field itself is dynamic. It drifts slowly over time. Magnetic north is not fixed at a single point. Occasionally, over thousands of years, the magnetic poles reverse entirely. These reversals are recorded in cooling lava and ocean crust, preserving a timeline of shifting magnetism. Despite such changes, life has endured. The magnetic field may weaken slightly during a reversal, but it does not vanish completely. Earth's atmosphere also provides protection, absorbing much of the radiation that penetrates the magnetic shield. Space may seem distant, but it influences the planet in subtle ways. Radiation from the Sun drives atmospheric chemistry. Solar cycles can slightly alter upper atmospheric temperatures. Even cosmic dust enters the atmosphere, burning as meteors and delivering tiny particles of material from beyond Earth. Every night, Earth travels through space. It orbits the Sun at about 67,000 miles per hour while spinning on its axis. Yet these motions are steady and predictable, creating day and night, seasons, and the passage of time. Above the calm sky you see tonight, magnetic lines are bending, solar particles are flowing past, invisible forces are interacting quietly beyond sight. And in this constant exchange between Earth and space, the planet remains protected, balanced, and moving steadily through the cosmos. Time on Earth is written not only in motion, but in layers. If you could slice through the crust and examine its cross-sections, you would see a record of environments long vanished, preserved one deposit at a time. Sedimentary rocks are among the clearest storytellers.
They form when particles settle out of water or air and accumulate in layers. Sand carried by rivers may gather along a coastline. Mud may settle in a quiet lake. Tiny shells of marine organisms may blanket the seafloor. Over time, pressure compacts these materials into stone. Each layer reflects conditions at the time it formed. A coarse layer might indicate strong currents or flooding. A fine layer could signal calm water. Fossils embedded within these rocks provide additional clues, revealing which organisms lived there and what the climate may have been. Some rock sequences show repeating patterns. Alternating layers of different colors or grain sizes can reflect seasonal cycles, shifting sea levels, or climate variations driven by changes in Earth's orbit. In this way, stone becomes a natural archive, storing rhythms of deep time. Not all rocks form from sediments. Igneous rocks crystallize from molten material. When lava cools at the surface, it forms fine-grained textures. When magma cools slowly underground, larger crystals have time to grow. These rocks reveal episodes of volcanic activity and tectonic movement. Metamorphic rocks tell a different story. They form when existing rocks are subjected to intense heat and pressure without fully melting. Minerals rearrange, creating new textures and patterns. The presence of certain minerals can indicate the depth and temperature at which transformation occurred. Together, these three rock types, sedimentary, igneous, and metamorphic, compose the rock cycle. Material moves from one form to another through burial, uplift, melting, and erosion. No rock is permanent. Given enough time, it can be broken down, transformed, and reformed elsewhere. Fossils add another dimension to the record. Impressions of leaves, bones of ancient creatures, and microscopic shells preserve moments of biological history. Some fossils are entire skeletons. Others are subtle chemical traces left behind by living organisms. Each provides insight into ecosystems that once thrived. Mass extinction events leave sharp boundaries in the rock record. Layers rich in certain elements, such as iridium from asteroid impacts, can mark sudden global change. Ash deposits from massive eruptions can be traced across continents, linking distant regions to the same event. Even tree rings and ice cores extend the timeline closer to the present. Annual growth rings reflect rainfall and temperature. Ice layers trap air bubbles that preserve ancient atmospheres. These records help scientists reconstruct past climates with surprising detail. The deeper you look into Earth's layers, the farther back you travel. Some of the oldest known rocks on continents are over 4 billion years old. They have survived countless cycles of erosion and tectonic change, remaining as fragments of Earth's earliest crust. Tonight, beneath your feet, layers of history remain stacked quietly below. Each one formed under skies that looked different from today. Each one carries a memory, and together they compose a slow, patient narrative written in stone. If you look closely at a single grain of sand, you are holding a fragment of deep time. That grain may have once been part of a mountain peak, lifted high by tectonic forces, then worn down by wind, water, and ice, until it became something small enough to rest in your palm. Mountains are born where plates converge. When continental crust collides, rock layers fold and thicken. Over millions of years, peaks rise toward the sky. Yet even as they rise, erosion begins its quiet work. Rain seeps into fractures, rivers cut valleys, glaciers scrape slopes, gravity pulls loosened rock downward. This balance between uplift and erosion shapes landscapes. In some regions, tectonic forces push upward faster than erosion can wear them down, creating towering ranges. In others, erosion gradually lowers peaks into rolling hills and plains. What appears permanent in a human lifetime is temporary in geological time. Sediment carries the story onward. As mountains erode, their fragments travel through river systems toward the sea. Sandstones, shales, and conglomerates form from these deposits. If buried deeply enough, heat and pressure may transform them into metamorphic rocks. If carried further into the mantle through subduction, they may melt and return as magma. Even the tallest peaks are part of this cycle. The Himalayas, still rising today, are built from crust that once lay beneath an ancient ocean. Marine fossils have been found high in these mountains, quiet reminders that environments can change dramatically over time. Weather patterns influence erosion rates. Regions with heavy rainfall often experience faster landscape change. In colder climates, freeze-thaw cycles widen cracks in rock. In arid deserts, wind carries fine particles that sandblast exposed surfaces, slowly sculpting cliffs and arches. Plants also shape mountains. Roots penetrate soil and rock, stabilizing slopes, but also contributing to weathering. Forests influence how water flows across the land, affecting erosion patterns. Even small organisms such as lichens break down minerals through chemical processes. Gravity never rests. Rockfalls, landslides, and avalanches redistribute material suddenly, reshaping slopes in moments. Though these events may seem dramatic, they are part of long-term adjustments as landscapes seek equilibrium. Isostasis adds another subtle effect. When large amounts of material are removed from a mountain range through erosion, the crust can rebound slightly upward, much like a floating object rising when weight is removed. This slow uplift can continue long after major tectonic forces have subsided. Over tens of millions of years, entire mountain ranges can vanish. What remains may be a stable craton, the ancient core of a continent. These regions often contain some of the oldest rocks on Earth, preserved from deep geological time. Yet the cycle does not end. New mountains will rise where plates meet. Old ones will erode away. Sediment will travel from highlands to lowlands, from rivers to oceans, and eventually back into the mantle. Tonight, while the landscape around you seems still, uplift and erosion continue quietly. The planet is shaping itself, one grain at a time.
Water does more than carve valleys and fill oceans. It cycles endlessly between sky, land, and sea, connecting every environment on Earth in a continuous exchange. The water cycle begins with evaporation. Sunlight warms oceans, lakes, and rivers, causing water molecules to rise into the atmosphere as vapor. Plants contribute as well through transpiration, releasing moisture from their leaves. Together, these processes send vast amounts of water into the air each day. As moist air rises, it cools. Cooler air holds less water vapor, so the vapor condenses into tiny droplets, forming clouds. High above, these droplets gather, sometimes joining with ice crystals.
When they grow large enough, gravity pulls them downward as precipitation. Rain, snow, sleet, or hail returns water to the surface. Some of it flows immediately across land as runoff, feeding streams and rivers. Some soaks into soil, replenishing groundwater stored in aquifers beneath the surface. Some becomes locked temporarily in snowpacks or glaciers. Groundwater moves slowly. Hidden below ground, it seeps through porous rock and sediment, sometimes emerging as springs. In arid regions, ancient groundwater may have been stored for thousands of years before reaching the surface again. The cycle is powered by solar energy. Without the sun's heat, evaporation would slow dramatically. Yet gravity plays a role, drawing water downhill and toward the ocean. The balance between solar energy and gravity keeps the cycle in motion. Water shapes climate. When water evaporates, it absorbs heat from its surroundings. When it condenses into clouds, it releases that heat into the atmosphere. This transfer of energy influences weather patterns and storm development. Large bodies of water moderate temperature. Because water warms and cools more slowly than land, coastal regions often experience milder seasonal changes. Oceans store heat during summer and release it gradually in winter, smoothing temperature extremes. Ice adds another dimension. When water freezes, it expands, making ice less dense than liquid water. This is why ice floats. Floating ice insulates the water below, allowing aquatic life to survive cold seasons. Ice sheets and glaciers also reflect sunlight, influencing global climate by affecting how much solar energy is absorbed. Over geological time, the distribution of water changes. During ice ages, large volumes of water become locked in ice sheets, lowering sea levels. When climates warm, melting ice raises sea levels and reshapes coastlines. Water also participates in chemical cycles. It dissolves minerals, transports nutrients, and facilitates reactions that influence the carbon cycle. Rivers carry dissolved elements to the sea, where they may become part of marine shells and sediments. Despite its constant movement, the total amount of water on Earth remains relatively stable. The same molecules that existed millions of years ago may be part of clouds today. The rain that falls tonight may once have flowed through ancient rivers or rested in glaciers long gone. As you breathe and rest, the water cycle continues quietly. Clouds drift, rivers flow, groundwater seeps unseen, and the planet's most essential substance moves steadily through its endless journey.
Ice has shaped Earth in ways that are easy to overlook. It moves slowly, almost imperceptibly, yet its influence reaches across continents and through deep time. Ice sheets begin where snowfall exceeds melting. Year after year, layers of snow compress under their own weight, transforming into dense ice. As thickness increases, gravity causes the ice to flow outward, not as a sudden slide, but as a slow, steady movement similar to thick liquid. This movement reshapes the land. As glaciers advance, they scrape bedrock beneath them, grinding stone into fine powder. They carve valleys into broad U-shapes, different from the sharp V-shaped valleys cut by rivers. Entire landscapes are smoothed, flattened, or hollowed by the passage of ice. When glaciers retreat,
they leave clear signatures behind. Long ridges of debris, called moraines, mark former ice margins. Scattered boulders carried far from their source rest quietly in unexpected places. Depressions left by melting ice may fill with water, forming lakes that dot many northern landscapes today. Ice ages have come and gone many times. These colder periods were not constant freezes, but cycles of advance and retreat driven by subtle changes in Earth's orbit and tilt. Small variations in sunlight distribution triggered large responses in ice coverage, demonstrating how sensitive the climate system can be. During ice ages, sea levels fell. As water became locked in continental ice sheets, oceans receded, exposing land bridges between continents. Animals and early humans used these pathways to migrate into new regions. When ice melted, rising seas submerged these routes again. Polar ice plays an ongoing role today. Ice sheets in Greenland and Antarctica store vast amounts of fresh water. Their bright surfaces reflect sunlight, helping regulate global temperatures. Changes in ice coverage can influence ocean circulation and atmospheric patterns worldwide. Sea ice behaves differently. It forms from frozen ocean water and expands and contracts with the seasons. Although thinner than land ice, it influences weather by insulating the ocean and reflecting solar energy. It also provides habitat for specialized ecosystems. Ice preserves history. Air bubbles trapped in ancient ice contain samples of past atmospheres. Layers within ice cores reveal snowfall patterns, volcanic eruptions, and temperature shifts going back hundreds of thousands of years. These frozen records allow scientists to reconstruct climate changes with remarkable detail. Even frozen ground, known as permafrost, shapes landscapes. In regions where soil remains frozen year-round, surface layers behave differently. When permafrost thaws, land can slump or collapse, altering drainage patterns and releasing stored carbon into the atmosphere. Despite its power, ice responds slowly. Glaciers do not rush. They move according to long-term balances between snowfall and melting. Their changes unfold over decades and centuries, often unnoticed until patterns become clear. Tonight, somewhere on Earth, ice is flowing. It is carving rock, reflecting sunlight, and storing memories of climates long past. And in its quiet persistence, ice continues to shape the planet, one slow movement at a time.
Deserts may appear empty, but they are landscapes shaped by subtle balance rather than absence. Defined not by heat alone, but by limited rainfall, deserts exist on every continent, including Antarctica. In many deserts, evaporation exceeds precipitation. Moisture that falls rarely lingers. Water quickly returns to the atmosphere, leaving behind minerals and salts. Over time, these deposits can create bright crusts across the ground, evidence of slow chemical processes unfolding beneath the sun. Wind becomes a dominant sculptor. Without dense vegetation to anchor soil, fine particles lift easily into the air. Sand grains bounce and skip across the surface in a motion called saltation, gradually shaping dunes. These dunes migrate slowly, responding to prevailing wind patterns over years and decades. Deserts are not static. Wind direction shifts. Occasional storms deliver intense but brief rainfall. Flash floods may surge through normally dry channels, carving temporary streams known as arroyos or wadis.
These sudden flows redistribute sediment and reshape terrain in moments. Temperature differences also play a role. Deserts often experience dramatic shifts between day and night. During the day, sunlight heats the surface rapidly. At night, heat escapes quickly into clear skies. This expansion and contraction stresses rock, contributing to mechanical weathering over time. Some deserts were once oceans. Marine fossils and layered sedimentary rocks reveal that regions now dry were previously underwater. As tectonic forces raised land and climate patterns shifted, these environments transformed entirely. Other deserts are shaped by rain shadows. When moist air rises over mountain ranges, it cools and releases precipitation. By the time the air descends on the other side, it is dry. The land beyond the mountains receives little rainfall, creating arid conditions even near coastlines. Life adapts quietly. Plants in deserts often conserve water through specialized leaves or deep roots. Some remain dormant for years, blooming only after rare rains. Animals may be nocturnal, avoiding daytime heat by moving under the cover of darkness. Dust connects deserts to distant ecosystems. Fine particles lifted by wind can travel across oceans. These dust plumes carry nutrients such as iron and phosphorus. When they settle, they fertilize soils or support marine life far from their origin. Even deserts record climate history. Layers of sand and sediment preserve patterns of past rainfall and wind intensity. Ancient lake beds hidden beneath desert surfaces indicate wetter periods in the past. The Sahara, for example, has alternated between green landscapes and dry expanses multiple times. Deserts are often quiet. Sound travels differently across open terrain. Without dense vegetation, wind whispers across sand, creating subtle patterns and low hums that shift with the breeze. Despite harsh conditions, deserts are part of Earth's interconnected system. They influence atmospheric circulation, reflect sunlight, and contribute to nutrient cycles. Their boundaries shift gradually as climates change over decades and centuries. Tonight, somewhere beneath a clear desert sky, dunes are moving slightly. Wind is carrying grains across open plains. And in that quiet motion, the desert continues its slow conversation with time.
Forests appear calm when you walk beneath them, yet they are dynamic systems shaped by soil, climate, and time. Trees rise slowly, drawing nutrients from the ground and carbon from the air, building structures that may stand for centuries. Soil is where the story begins. It forms from the breakdown of rock combined with organic material from plants and animals. This process takes time. In some regions, it may require hundreds or even thousands of years to build only a few inches of fertile ground. Beneath the forest floor lies a layered system of minerals, roots, microbes, and moisture. Roots anchor trees, but also communicate. Through networks of fungi attached to their roots, many trees exchange nutrients and chemical signals. These underground connections allow forests to behave less like isolated individuals and more like interwoven communities. Leaves capture sunlight. Through photosynthesis, trees convert carbon dioxide and water into energy, releasing oxygen as a byproduct. Forests, therefore, play a significant role in regulating atmospheric composition. They act as carbon sinks, storing carbon within wood, leaves, and soil.
Forests also influence climate locally. Through transpiration, trees release water vapor into the air. This moisture can contribute to cloud formation and rainfall. In large forest systems, such as tropical rainforests, this recycling of water supports regional weather patterns. Different forests reflect different climates. Tropical rainforests grow where warmth and rainfall are abundant year-round. Temperate forests experience seasons, with leaves changing color and falling in autumn. Boreal forests stretch across northern latitudes, where cold winters and short growing seasons limit tree variety. Fire is part of many forest cycles. Though destructive in appearance, some ecosystems depend on periodic fires to clear undergrowth and release nutrients back into the soil. Certain tree species even require heat from fire to open their cones and release seeds. Storms also reshape forests. Strong winds can topple trees, creating openings in the canopy. These gaps allow sunlight to reach the forest floor, encouraging new growth. Over time, forests renew themselves through such disturbances. Animal life is deeply intertwined with forests. Birds nest in branches, insects pollinate flowers, mammals disperse seeds. Each organism contributes to nutrient cycling and ecosystem balance. Even fallen leaves become food for decomposers that return nutrients to the soil. Over long periods, forests migrate. As climates shift, tree populations gradually move toward favorable conditions. Fossil pollen found in sediment layers reveals how forests expanded and retreated during past ice ages. Yet forests are not permanent. They depend on stable climates, adequate moisture, and healthy soils. Changes in temperature or rainfall can alter species composition over time. Tonight, in forests across the planet, leaves are exchanging gases with the air. Roots are drawing water upward. Tiny organisms in the soil are breaking down fallen matter. The forest may appear still, but beneath its quiet canopy, countless processes continue steadily. And in that balance between growth, decay, and renewal, forests remain one Earth's most intricate living systems.
Grasslands stretch wide beneath open skies, often overlooked because they lack towering trees or dramatic cliffs. Yet these landscapes are shaped by powerful forces and play a vital role in Earth's balance. Grasslands form where rainfall is enough to support vegetation, but not enough to sustain dense forests. In these regions, grasses dominate. Their growth patterns differ from trees. Instead of investing energy in tall trunks, grasses spread outward and downward, building extensive root systems beneath the soil. Those roots are essential. They anchor soil against erosion and store significant amounts of carbon underground. In fact, much of a grassland's biomass lies below the surface, hidden from view. Even if fire sweeps across the land, the roots often survive and regenerate quickly. Fire is a natural part of many grassland ecosystems. Lightning strikes or dry conditions can ignite grasses, clearing accumulated plant material. These periodic fires prevent shrubs and trees from taking over, maintaining the open character of the landscape. Large herbivores also shape grasslands. Animals such as bison, antelope, and wild horses graze on grasses, influencing plant growth and distribution. Their movement redistributes nutrients across the land. Through grazing and migration, they contribute to ecosystem resilience. Wind plays a steady role as well. Across open plains, wind can move freely,
shaping weather patterns and carrying seeds. In some regions, wind-blown sediments known as loess accumulate over time, forming fertile soils that later support agriculture. Grasslands often experience seasonal extremes. Winters may be cold, summers hot. Rainfall can vary from year to year. Plants adapted to these conditions grow rapidly during favorable periods and remain dormant during drought. Many grasslands have deep soils. Because grasses die back annually, their decaying roots add organic material to the ground. Over centuries, this builds thick, nutrient-rich layers. Some of the world's most productive agricultural regions developed from ancient grasslands. Grasslands also influence climate. Their reflective surfaces absorb and release heat differently than forests. The carbon stored in their soils contributes to the global carbon cycle, helping regulate atmospheric composition. In certain regions, grasslands transition gradually into deserts or forests. These transitional zones shift over time depending on rainfall patterns and temperature changes. A slight increase in moisture may encourage tree growth. A decrease may push the boundary toward arid conditions. Even small organisms are vital here. Insects pollinate wildflowers. Burrowing animals aerate the soil. Microbes break down organic matter, cycling nutrients through the ecosystem. Though they may appear simple, grasslands are dynamic. They respond to fire, grazing, rainfall, and climate variability. Their open expanses allow sweeping views of sky and horizon where weather patterns unfold visibly across vast distances. Tonight, winds move softly across plains somewhere on Earth. Grasses bend and rise again. Roots hold soil firmly in place. And in that steady balance between growth and disturbance, grasslands continue quietly, shaping and sustaining life across wide open spaces. Coastlines are places of meeting. Land and sea converge in shifting boundaries that are never entirely fixed. Though a shoreline may seem stable within a lifetime, it is constantly adjusted by waves, tides, and changes in sea level. Waves begin far from shore. Wind blowing across the surface of the ocean transfers energy into the water. That energy travels as swells across vast distances. In deep water, waves may pass unnoticed beneath ships, but as they approach shallow coastal zones, their motion changes. The base of the wave begins to feel the ocean floor. Friction slows the lower portion while the top continues forward. This causes the wave to steepen and eventually break, releasing its energy onto the shore. With each breaking wave, sediment is lifted, moved, and rearranged. Sand rarely stays in one place. Along many coasts, waves approach at slight angles. This creates longshore currents that transport sand parallel to the beach. Over time, this steady drift can build barrier islands, sand spits, and wide stretches of beach far from the sediment's original source. Cliffs tell a different story. Where coastlines are made of harder rock, waves gradually undercut their base. Sections collapse and fall into the sea. The debris may then be ground into smaller particles, eventually becoming sand or gravel along other shores. Tides add rhythm to this movement. Driven primarily by the moon's gravity, tides raise and lower water levels daily. In some regions, tidal ranges are small. In others, water levels shift dramatically, exposing wide tidal flats at low tide and covering them again at high tide. Sea level itself is not constant. During ice ages, vast quantities of water were locked into glaciers, lowering global sea levels. When ice melted, seas rose and flooded coastal plains. Ancient shorelines now lie submerged beneath modern waters,
while raised beaches stand high above present sea level in some regions. Coral reefs shape tropical coastlines. These living structures, built by tiny organisms, grow slowly over centuries. They act as natural breakwaters, reducing wave energy before it reaches land. Over time, coral fragments can contribute to sandy beaches and island formation. Storms can alter coasts quickly. Hurricanes and cyclones push storm surges toward land, eroding beaches and reshaping barrier islands in a matter of hours. Yet even these dramatic events are part of long-term coastal evolution. Human structures interact with natural processes. Seawalls, jetties, and harbors can interrupt sediment transport, causing erosion in some areas and buildup in others. Coastlines respond dynamically to both natural forces and human influence. Despite constant change, coasts support rich ecosystems. Tidal marshes, mangroves, and estuaries provide habitat for countless species. These environments filter water, absorb wave energy, and store carbon in sediments. Tonight, somewhere along a distant shore, waves are rolling in softly. Sand is shifting, grain by grain. Tides are rising and falling under lunar pull. And in that gentle, persistent motion, coastlines continue their quiet negotiation between land and sea.
Beneath Earth's surface lies heat that has never fully faded. This internal energy, left over from the planet's formation and fueled partly by radioactive decay, continues to influence landscapes in subtle and dramatic ways. Volcanoes are one of the clearest expressions of this hidden warmth. They form where magma, generated deep within the mantle, finds pathways toward the surface. Sometimes this occurs along plate boundaries, where subduction or rifting creates openings. In other cases, magma rises through thinner regions of crust far from plate edges. When magma reaches the surface, it becomes lava. Its behavior depends on its composition. Some lava flows easily, spreading in long rivers before cooling into dark basalt. Other lava is thicker and more resistant to movement, building steep-sided volcanoes over time. Volcanic eruptions vary greatly. Some are quiet, releasing lava slowly. Others are explosive, sending ash and gas high into the atmosphere. Ash clouds can travel across continents, influencing climate temporarily by reflecting sunlight. Yet even after eruptions cease, volcanic landscapes remain active. Hot springs, geysers, and fumaroles release steam and gases from below. These geothermal features reveal that heat continues to move upward, even if lava no longer flows visibly. Geothermal energy also shapes chemistry. Water heated underground dissolves minerals from surrounding rock. When it emerges at the surface and cools, those minerals may precipitate, forming colorful deposits or crystalline structures. Volcanic soil can be remarkably fertile. Over time, weathered volcanic rock releases nutrients that support plant growth. Some of the world's most productive agricultural regions lie near former volcanic activity. Volcanoes also contribute gases to the atmosphere. Throughout Earth's history, volcanic emissions helped shape atmospheric composition. While large eruptions can temporarily cool global temperatures by injecting particles into the stratosphere, volcanic carbon dioxide also plays a role in long-term climate cycles. Underwater volcanoes are even more numerous. Along mid-ocean ridges and seamount chains, magma rises continuously, forming new crust in darkness. These eruptions often go unnoticed by human observers, yet they represent one of the planet's most active construction processes. Hotspots create volcanic chains. In certain regions, plumes of heat rise from deep within the mantle. As tectonic plates move above these plumes, a series of volcanoes can form in a line. The Hawaiian Islands are one example of this process in motion. Even long dormant volcanoes are part of Earth's rhythm. Some remain quiet for centuries before becoming active again. Others gradually erode into rounded hills, their fiery origins softened by time. Despite their dramatic reputation, volcanoes are part of a larger system. They release internal heat, recycle crustal material, and influence atmospheric chemistry. They remind us that Earth's interior remains dynamic. Tonight, somewhere on the planet, magma is moving slowly through cracks in rock. Steam is rising from heated springs. The deep interior continues its patient circulation. And beneath the still surface you see, Earth's ancient warmth quietly endures.
Earthquakes are sudden reminders that the planet's surface is divided into moving pieces. Yet the forces behind them build gradually, often over decades or centuries, long before any shaking is felt. Tectonic plates rarely move smoothly past one another. Along faults, edges of plates can become locked due to friction. Though the plates continue to push, the fault resists motion. Stress accumulates slowly within the surrounding rock. Eventually, the stress exceeds the strength of the rocks holding it back. When that threshold is crossed, the fault slips. Stored energy is released in waves that travel outward through the crust. These seismic waves move in different patterns, some compressing material as they pass, others shifting it side to side. The point within the Earth where movement begins is called the focus. Directly above it, on the surface, lies the epicenter. Shaking intensity decreases with distance, but local geology also influences how strongly an area feels the motion. Not all earthquakes are large. Many occur daily and are too small to be noticed without instruments. Sensitive seismographers record these subtle vibrations, helping scientists map fault systems and understand plate boundaries. Different types of plate interactions create different earthquake patterns. At convergent boundaries, where plates collide, powerful quakes can occur as one plate slides beneath another. At transform boundaries, where plates move sideways past each other, shallow earthquakes are common. Even within plate interiors, stresses can build and release unexpectedly. Earthquakes reshape landscapes. Ground can shift horizontally or vertically. Rivers may change course. Landslides can be triggered by shaking, moving large volumes of rock downslope. In coastal areas, underwater quakes may displace water and generate tsunamis. Tsunamis differ from regular ocean waves. They are caused by sudden vertical displacement of the seafloor. In deep water, they may pass unnoticed, traveling at high speeds across ocean basins. As they approach shallow shores, their height increases, sometimes dramatically. Despite their sudden nature, earthquakes are part of a long cycle. The release of stress allows plates to continue moving. Over time, new stresses accumulate and the process repeats. This pattern, known as the earthquake cycle, reflects the ongoing motion of tectonic plates. Scientists cannot predict the exact moment of a quake. However, they study fault behavior, historical patterns, and plate movements to assess risk. Preparedness and resilient infrastructure reduce potential harm when shaking does occur. Earthquakes also reveal information about the planet's interior.
Seismic waves change speed and direction depending on the materials they pass through. By analyzing these changes, scientists have mapped Earth's layered structure, identifying the crust, mantle, and core. Tonight, while you rest, plates continue their slow movement. Somewhere, stress may be building along a fault. Elsewhere, small tremors may be releasing energy gently. Beneath the calm ground you stand on, the planet remains in motion, steady and powerful, adjusting itself through cycles of tension and release that have continued for millions of years.
Far above mountains and oceans, high in the upper atmosphere, tiny particles drift in delicate balance. Though nearly invisible, these particles influence sunlight, temperature, and even the colors of the sky. Aerosols are small, solid, or liquid particles suspended in air. They come from many sources. Sea spray lifts salt into the atmosphere. Desert winds carry dust across continents and oceans. Volcanic eruptions inject ash and sulfur-rich gases high above the clouds. Even forest fires release fine particles that can travel long distances. Some aerosols reflect sunlight. When tiny droplets or dust scatter incoming solar radiation, a portion of that energy is redirected back into space. This can create a slight cooling effect at the surface. After major volcanic eruptions, global temperatures may drop temporarily due to the presence of reflective particles in the stratosphere. Other particles absorb heat. Dark-colored soot, for example, can capture solar energy and warm the surrounding air. The balance between reflective and absorptive particles influences climate in subtle ways. Cloud formation depends on aerosols as well. Water vapor in the atmosphere requires tiny surfaces on which to condense. Aerosols provide those surfaces, acting as cloud condensation nuclei. Without them, cloud droplets would have difficulty forming. Clouds themselves regulate temperature. They reflect sunlight during the day and trap outgoing heat at night. Their thickness, altitude, and composition determine how they influence energy balance. High, thin clouds may allow sunlight through while trapping heat below. Low, thick clouds often reflect more sunlight than they retain. The sky's colors are shaped by scattering. When sunlight passes through the atmosphere, shorter blue wavelengths scatter more than longer red wavelengths. This scattering gives the daytime sky its blue appearance. At sunrise and sunset, when sunlight travels through more atmosphere, reds and oranges dominate. Upper atmospheric layers respond to solar activity. During periods of heightened solar energy, the upper atmosphere can expand slightly as it absorbs more radiation. This subtle expansion influences satellite orbits and space debris behavior. Even meteors contribute. Tiny fragments of rock entering Earth's atmosphere burn up, adding microscopic particles to the upper layers. Though individually small, over long periods, these additions become part of the atmospheric system. The atmosphere also interacts with Earth's magnetic field. Charged particles guided toward polar regions produce auroras, lighting the sky in shifting curtains. These events demonstrate how closely Earth is linked to space beyond its surface. Despite its complexity, the atmosphere remains thin. If Earth were the size of an apple, the breathable layer would be thinner than its skin. Yet within that narrow band, weather forms,
sunlight scatters, and life thrives. Tonight, particles drift high above you. Clouds are forming somewhere over distant seas. Sunlight is being reflected, absorbed, and scattered in quiet balance. And in that fragile envelope of air, Earth maintains the delicate conditions that make the planet not only dynamic, but habitable.
Deep beneath the crust and mantle lies Earth's core, a region unreachable by direct observation, yet central to the planet's behavior. Though hidden thousands of miles below, its presence influences everything from magnetic fields to surface stability. The core is divided into two parts. The outer core is liquid, composed primarily of iron and nickel. Beneath it lies the inner core, solid despite extremely high temperatures. The immense pressure at such depths prevents the inner core from melting, even though temperatures there rival the surface of the sun. Heat drives motion within the outer core. As Earth slowly cools, heat escapes from the inner core outward. This movement, combined with Earth's rotation, creates circulating currents of molten metal. Because iron conducts electricity, these moving currents generate Earth's magnetic field through a process known as the geodynamo. The magnetic field extends far beyond the surface. It forms a protective region that shields the planet from much of the solar wind. Without it, charged particles from the sun could gradually strip away portions of the atmosphere, as likely happened on Mars long ago. The core also influences plate tectonics. Heat rising from deep within the planet contributes to mantle convection. This slow circulation in the mantle drives the movement of tectonic plates at the surface. Though the connection is indirect, the energy source originates far below. Seismic waves reveal the core's structure. When earthquakes occur, the waves they produce travel through Earth's layers. Some waves cannot pass through liquid, while others bend or reflect differently depending on material density. By analyzing these patterns, scientists have mapped the boundaries between crust, mantle, outer core, and inner core. The inner core may not be uniform. Some research suggests it rotates slightly differently from the rest of the planet, though at a very slow rate. Variations in its structure hint at complex processes unfolding over billions of years. Radioactive decay contributes to internal heat. Elements such as uranium, thorium, and potassium release energy as they decay, adding to the heat left over from Earth's formation. This energy helps sustain mantle convection and magnetic field generation. The magnetic field itself is dynamic. It drifts over time and occasionally reverses polarity. Evidence of these reversals is preserved in ancient rocks, which recorded the direction of the magnetic field when they cooled. Despite constant activity, the core remains beyond direct reach. Drilling projects have penetrated only a tiny fraction of Earth's crust. Everything known about the core comes from indirect measurements, seismic data, and theoretical modeling. Yet its influence is unmistakable. Compasses align with magnetic lines created deep within. Auroras shimmer because of interactions between solar particles and magnetic fields. Tectonic plates move because heat rises from below. Tonight, while the surface seems calm, molten metal is flowing thousands of miles beneath you. Heat is transferring outward. Magnetic fields are bending invisibly through space. And in that hidden realm, Earth's core continues its steady, essential work. Earth's climate is not fixed.
Over millions of years, it has shifted between warmer and cooler states, shaped by a combination of orbital patterns, atmospheric chemistry, ocean circulation, and geological activity. One major influence comes from Earth's orbit. The planet does not travel around the Sun in a perfect circle. Its orbit varies slightly in shape over tens of thousands of years. At times, it becomes more elliptical, at others, more circular. These changes alter how sunlight is distributed across the planet. Earth's axis also shifts. Currently tilted at about 23.5 degrees, the axis wobbles slowly over long cycles. Small variations in tilt influence the intensity of seasons. When tilt increases, seasonal contrasts become stronger. When it decreases, seasons become milder. Precession adds another layer. This slow wobble changes the timing of seasons relative to Earth's position in its orbit. Together, these orbital variations are known as Milankovitch cycles. Though subtle, they have played a role in pacing past ice ages. Atmospheric composition influences climate as well. Greenhouse gases such as carbon dioxide and methane trap heat in the lower atmosphere. Without them, Earth would be much colder. However, changes in their concentration can shift global temperatures over time. Volcanic activity sometimes affects climate temporarily. Large eruptions can send sulfur-rich particles into the stratosphere, reflecting sunlight and cooling the surface for a few years. Over longer timescales, volcanic emissions contribute carbon dioxide that influences warming trends. Ocean circulation connects climate systems. The global conveyor belt of deep ocean currents redistributes heat between equatorial and polar regions. Changes in salinity or temperature can alter this circulation, affecting regional climates. Continental positions matter too. When landmasses cluster near the poles, ice sheets may grow more easily. When continents gather near the equator, ocean circulation and wind patterns shift. The arrangement of land and sea influences both rainfall and temperature distribution. Feedback loops amplify change. For example, when ice expands, it reflects more sunlight, promoting further cooling. When ice melts, darker surfaces absorb more heat, accelerating warming. These feedbacks can intensify climate shifts. Life also interacts with climate. Plants absorb carbon dioxide through photosynthesis. Marine organisms influence carbon storage in sediments. Over geological time, biological processes have helped regulate atmospheric composition. Ice cores and sediment records preserve climate history. Layers of ice trap air bubbles that reveal past greenhouse gas levels. Ocean sediments record temperature changes and biological shifts. Together, these records show that climate has always evolved. Tonight, Earth continues its long cycles. Sunlight falls unevenly across the surface. Oceans move heat between hemispheres. Atmospheric gases trap warmth in a delicate balance. Climate change may unfold gradually or more abruptly, but it is part of the planet's dynamic nature. And beneath the steady rhythm of day and night, Earth's climate system remains in motion, shaped by forces both subtle and profound. Life and geology are more closely connected than they first appear. The planet's surface and its living systems have influenced one another for billions of years, shaping conditions in ways both subtle and profound. One of the earliest examples is photosynthesis. When microscopic organisms began using sunlight to produce energy, they released oxygen into the atmosphere. Over time, oxygen accumulated, transforming Earth's air and oceans. This event, sometimes called the Great Oxygenation, altered mineral chemistry worldwide. Iron dissolved in ancient oceans reacted with oxygen. The result was the formation of banded iron formations, layered rocks that record the gradual increase of oxygen in seawater. These deposits remain as evidence of life reshaping planetary chemistry. Plants later expanded onto land. As roots penetrated rock, they accelerated weathering. Chemical reactions between minerals and carbon dioxide removed carbon from the atmosphere and stored it in sediments. This process contributed to long-term climate regulation. Coral reefs demonstrate another partnership. Tiny coral polyps build calcium carbonate skeletons, forming massive reef structures over centuries. These reefs protect coastlines from wave energy and create habitats for diverse marine life. Their growth also locks carbon into solid form. Marine organisms influence global carbon cycles. When plankton die, some of their remains sink to the ocean floor. Over time, this organic material may become buried in sediments, storing carbon away from the atmosphere for millions of years. Even microorganisms in soil play a role. Bacteria and fungi decompose organic matter, recycling nutrients back into ecosystems. Through respiration and decomposition, they influence atmospheric gas levels. Large forests affect rainfall patterns. Through transpiration, trees release moisture into the air, contributing to cloud formation. In extensive forest regions, this recycled moisture helps sustain regional precipitation cycles. Life also responds to geological change. When continents shift, species adapt or migrate. Mountain building creates new climates and habitats. Volcanic eruptions may disrupt ecosystems, yet they also create fertile soils that support future growth. Mass extinctions illustrate the delicate balance between life and environment. Asteroid impacts, volcanic eruptions, and climate shifts have eliminated large portions of Earth's species at various times. Yet after each event, life has recovered and diversified in new directions. Even today, biological processes interact with geology. Wetlands store carbon in waterlogged soils. Shell-forming organisms extract minerals from seawater. Plant roots stabilize slopes and reduce erosion. The biosphere and geosphere are not separate systems. They form a complex network of interactions where chemistry, climate, and life continuously influence one another. Tonight, forests are exchanging gases with the atmosphere. Plankton are drifting near the ocean's surface. Microbes are breaking down organic matter in soil. These quiet processes shape the air you breathe and the landscapes you see. And through this constant exchange between living organisms and solid Earth, the planet maintains a balance that has evolved over deep time, steady and interconnected.
Deep time can be difficult to imagine. Human history spans only a tiny fraction of Earth's existence. If the planet's 4.5 billion year story were compressed into a single calendar year, complex life would appear only in the final weeks, and human civilization in the final seconds before midnight. Rocks preserve this immense timeline. Some of the oldest minerals found on Earth are tiny zircon crystals, more than 4 billion years old. These crystals formed when the planet was still young, offering clues about early crust and the presence of liquid water. Continental cores, known as cratons, contain some of the oldest stable rock.
These regions have survived countless cycles of collision and erosion. Though mountains may rise and fall around them, cratons endure as ancient anchors within continents. Oceanic crust tells a different story. Unlike continental rock, seafloor is continuously recycled. At mid-ocean ridges, new crust forms. At subduction zones, older crust sinks back into the mantle. This recycling keeps most oceanic rock relatively young compared to continental interiors. Supercontinents have assembled and broken apart multiple times. Before Pangaea, earlier supercontinents such as Rodinia and Columbia existed. Each assembly reshaped climate, ocean circulation, and biological evolution. When continents join, interior regions may become dry. When they separate, new coastlines form and ecosystems diversify. Fossils reveal the progression of life. Simple single-celled organisms dominated for billions of years. Multicellular life appeared later, followed by a rapid diversification known as the Cambrian explosion. Over time, plants colonized land, insects evolved, and vertebrates adapted to new environments. Mass extinctions punctuate this history. The most severe, occurring about 252 million years ago, eliminated a large percentage of marine and terrestrial species. Yet life recovered, evolving into new forms that filled empty ecological niches. Ice ages, warm periods, volcanic outpourings, and asteroid impacts all left marks in the geological record. Layers of sediment and volcanic ash act as timestamps, allowing scientists to align events across continents. Radiometric dating provides precise ages. By measuring the decay of radioactive isotopes within minerals, scientists determine when rocks formed. This method has established Earth's age with remarkable accuracy. Time is recorded not only in rock, but also in landscapes. Eroded mountain ranges hint at former heights. Ancient river terraces mark previous water levels. Fossil coral reefs found inland reveal past sea levels. Even the magnetic field leaves a timeline. As lava cools, iron minerals align with the current magnetic direction. When the field reverses, new lava records the change. Ocean floor stripes preserve this pattern of reversals, confirming seafloor spreading. Tonight, beneath modern cities and forests, layers of rock extend downward through vast spans of time. Each layer represents environments long gone, climates once dominant, and life forms that no longer exist. And as Earth continues its slow transformation, new layers are being added, quietly extending the record into the future.
Earth is not isolated in its journey. It moves within a larger solar system, influenced by gravity, radiation, and subtle interactions with neighboring bodies. Though the planet feels grounded and stable, it is part of a vast celestial dance. Earth orbits the Sun once every year. This motion defines the length of our calendar and governs the rhythm of seasons. Because Earth's axis is tilted, different regions receive varying amounts of sunlight throughout the year. When one hemisphere tilts toward the Sun, it experiences summer, while the opposite hemisphere enters winter. The orbit itself is not perfectly circular. It shifts slightly in shape over long timescales. These variations influence how sunlight is distributed across latitudes, contributing to long-term climate patterns. The moon exerts a steady influence.
Its gravitational pull generates tides, subtly stretching the oceans and even the solid crust. Over time, tidal friction has gradually slowed Earth's rotation. Billions of years ago, days were shorter. The planet has been lengthening its rotation period slowly ever since. Meteorites occasionally reach the surface. Most are small and burn up in the atmosphere, appearing briefly as streaks of light. Larger impacts have occurred in the past, leaving craters that may be hidden by erosion or buried beneath sediments. Some impacts have altered global climate and ecosystems. Solar radiation powers life. Light energy drives photosynthesis, warming land and sea. Yet the sun's output is not perfectly constant. It follows cycles of activity, with periods of greater and lesser intensity. These variations can influence upper atmospheric conditions and magnetic interactions. Beyond the sun and moon, gravity from other planets exerts subtle effects. Though distant, massive planets like Jupiter influence the motion of smaller bodies. Their gravity helps shape asteroid belts and can deflect objects that might otherwise approach Earth. Earth also moves through the galaxy. It orbits the center of the Milky Way over hundreds of millions of years. During this journey, the solar system passes through different regions of interstellar space, though these changes occur over immense timescales. Cosmic radiation interacts with the atmosphere. High-energy particles from distant sources collide with atmospheric molecules, creating cascades of secondary particles. Most are absorbed before reaching the surface, filtered by atmospheric thickness and magnetic shielding. Despite these cosmic influences, Earth maintains a delicate balance. Its distance from the sun allows liquid water to exist. Its magnetic field shields it from much radiation. Its atmosphere moderates temperature. These conditions make the planet uniquely hospitable. Tonight, as you rest, Earth is spinning on its axis, orbiting the sun and traveling through space simultaneously. The stars overhead appear still, but the entire system is in motion. And within this vast cosmic journey, Earth continues to sustain oceans, forests, deserts, and life, quietly moving through the universe while maintaining the conditions that make it home.
Beneath forests, deserts, mountains, and cities lies a hidden system of stored water that moves so slowly it is rarely noticed. Groundwater fills tiny spaces within rock and sediment, forming underground reservoirs known as aquifers. When rain falls, not all of it flows into rivers. Some water seeps into the soil, moving downward through pores and fractures. If it reaches layers of permeable rock, it may continue descending until it meets a less permeable barrier. There, water accumulates, filling the spaces between grains. This stored water can remain underground for years, decades, or even millennia. Some aquifers contain ancient water that fell as rain during past climates very different from today's. In arid regions, groundwater may be a remnant of wetter periods long ago. Aquifers vary in size and depth. Some lie close to the surface and recharge quickly with seasonal rainfall. Others are buried deep and recharge very slowly. The rate of replenishment depends on rainfall, soil composition, and the permeability of underlying rock. Groundwater moves quietly. Unlike rivers, it does not rush. It seeps at rates that may be measured in inches or feet per day. Eventually, it may emerge as springs, feeding streams even during dry seasons. The interaction between groundwater and surface water is constant. Rivers can recharge aquifers during high flow periods. In turn, groundwater can sustain rivers when rainfall is scarce.
This exchange maintains ecosystem stability in many regions. Groundwater also shapes landscapes. Over time, slightly acidic water can dissolve limestone, creating underground caves and sinkholes. Entire cave systems form from this slow chemical weathering, carving intricate chambers beneath the surface. In coastal areas, freshwater aquifers sit above denser saltwater. If too much groundwater is removed, saltwater can move inland, altering water chemistry. This delicate balance illustrates how interconnected subsurface systems are with surface conditions. Water stored underground plays a role in agriculture and human settlement. Many communities rely on wells tapping into aquifers. Sustainable use requires understanding how quickly groundwater replenishes and how slowly it may move. Even temperature varies underground. Below a certain depth, temperature increases steadily due to Earth's internal heat. In some regions, geothermal energy can be harnessed from warm groundwater. Groundwater also carries dissolved minerals. As water moves through rock, it interacts chemically, picking up elements that influence taste and composition. These dissolved minerals can later precipitate in caves, forming stalactites and stalagmites over long periods. Despite its importance, groundwater remains unseen. It flows beneath fields, cities, forests, and plains. It connects rainfall from distant hills to springs emerging miles away. Tonight, while rivers move visibly across the land, groundwater is also in motion below your feet, slowly seeping, dissolving, storing, and emerging. And in its quiet journey through hidden channels, it continues to shape landscapes and sustain life in ways rarely noticed, yet profoundly essential.
Not all of Earth's history is written in rock layers or fossils. Some of it is recorded in subtle chemical signatures, tiny variations in elements that reveal how environments once functioned. Isotopes are different forms of the same element. They share the same number of protons but differ in neutrons. Some isotopes are stable, while others are radioactive and decay over time. By studying isotope ratios in rocks, ice, and sediments, scientists uncover clues to past climates and geological events. Oxygen isotopes are especially informative. Water molecules containing slightly heavier oxygen behave differently during evaporation and condensation. During colder periods, more of the heavier isotope remains in oceans, while lighter forms become locked in ice sheets. By measuring these ratios in ice cores or marine shells, scientists estimate past temperatures. Carbon isotopes tell another story. Photosynthetic organisms prefer lighter carbon isotopes. When large amounts of organic material are buried, the balance of carbon isotopes in the atmosphere shifts. These variations appear in sedimentary rocks and provide insight into biological productivity across time. Strontium isotopes reflect tectonic activity. When mountains rise and erode, minerals release strontium into rivers and eventually into oceans. The ratio of strontium isotopes preserved in marine sediments can indicate periods of intensified mountain building or continental weathering. Even tiny bubbles in ice cores preserve atmospheric composition. As snow accumulates and compresses into ice, it traps air. These bubbles contain samples of ancient atmospheres, allowing scientists to measure greenhouse gas concentrations from tens of thousands of years ago. Trace elements in ocean sediments reveal circulation patterns. Certain chemical signatures indicate how deep water moved and where nutrients accumulated. These patterns help reconstruct ancient ocean currents and climate conditions. Volcanic ash layers serve as chemical markers.
Each eruption has a distinct composition. When ash spreads across wide areas, it creates a time-stamped layer that links distant sediment records to the same event. Magnetic minerals also preserve information. As molten rock cools, iron-bearing minerals align with the current magnetic field. These alignments record past reversals and plate movements, providing a timeline for tectonic processes. Even cave formations carry chemical archives. Stalactites and stalagmites grow from dripping mineral-rich water. Their layers reflect changes in rainfall and vegetation above ground. By analyzing these layers, scientists reconstruct regional climate shifts over centuries or millennia. Chemical evidence extends beyond Earth. Meteorites contain isotopic signatures older than the planet itself. These grains reveal processes that occurred in ancient stars before the solar system formed. Though invisible to the eye, these chemical fingerprints are powerful tools. They transform stone, ice, and sediment into detailed records of environmental change. Tonight, while landscapes appear still, chemical exchanges continue. Water dissolves minerals, plants absorb carbon, isotopes shift in subtle balance. And within these tiny variations lies a quiet archive of Earth's evolving story, preserved not in grand formations, but in the smallest measurable differences. Earth's surface may seem solid and complete, yet it is part of a much larger exchange of matter and energy that extends beyond the visible landscape. Elements move continuously between air, water, soil, rock, and living organisms in cycles that sustain life. The carbon cycle is one of the most essential. Carbon exists in the atmosphere as carbon dioxide, in oceans as dissolved carbonate, in rocks as limestone, and in living organisms as organic molecules. Plants absorb carbon dioxide during photosynthesis, incorporating it into tissues that may later decompose or become buried. When organisms respire, carbon returns to the air. When marine life forms shells, carbon becomes locked in calcium carbonate. Over time, these shells accumulate on the ocean floor, forming limestone. Through tectonic uplift and weathering, carbon can eventually re-enter the atmosphere, completing a slow geological loop. The nitrogen cycle operates differently. Most nitrogen exists in the atmosphere as a stable gas that plants cannot use directly. Specialized bacteria convert atmospheric nitrogen into forms that plants can absorb. Animals then obtain nitrogen by consuming plants or other animals. When organisms die, decomposers return nitrogen to the soil. Some bacteria convert it back into atmospheric form, maintaining balance. This cycle supports the building blocks of proteins and DNA, essential to life. Phosphorus follows yet another path. Unlike carbon and nitrogen, phosphorus does not circulate significantly through the atmosphere. It moves primarily through rock, soil, water, and living systems. Weathering releases phosphorus from rock, allowing plants to absorb it. Through food webs, it travels between organisms. Eventually, phosphorus may wash into rivers and oceans. There, it becomes part of marine sediments. Over geological time, tectonic uplift may reintroduce phosphorus to land ecosystems. Even trace elements participate in cycles. Iron, essential for many biological processes, can be carried by wind-blown dust across oceans. When it settles in nutrient-limited waters, it can stimulate plankton growth, linking deserts to marine productivity. Energy flows alongside these elements. Sunlight enters the system, driving photosynthesis. Organisms convert that energy into chemical form. When organisms consume one another, energy transfers upward through food chains. Ultimately, energy dissipates as heat, radiating back into space. Though elements cycle continuously, the quantities remain relatively stable. Atoms that were part of ancient forests may now exist in modern organisms. Water that once flowed through prehistoric rivers may fall again as rain. These cycles operate quietly and persistently. They connect volcanoes to oceans, forests to atmosphere, microbes to mountains. They demonstrate that Earth is not a collection of separate systems, but a network of ongoing exchanges. Tonight, carbon is moving through leaves, nitrogen is cycling through soil, phosphorus is traveling toward distant seas, and within this intricate circulation of matter and energy, the planet sustains balance, linking every environment through processes that never truly pause.
Earth's story does not end with the present moment. The same processes that shaped its past continue quietly into the future. Continents are still moving, oceans are still circulating, and climates are still shifting in response to forces both internal and external. Plate tectonics will not stop. Millions of years from now, the continents we recognize today will have drifted into new positions. The Atlantic Ocean may widen further, while other oceans gradually shrink as plates converge elsewhere. New mountain ranges will rise where collisions occur. Older ranges will erode into gentle highlands. Some scientists suggest that another supercontinent may form in the distant future. If current plate motions continue, land masses could gather once again into a single vast region. Such a reassembly would alter ocean circulation, climate patterns, and habitats across the globe. Volcanic activity will persist. Hotspots will continue building islands as plates pass overhead. Subduction zones will generate volcanic arcs. While individual eruptions may be brief, the overall process of crust creation and recycling will endure. Climate will evolve as well. Orbital cycles will keep influencing the distribution of sunlight. Ice sheets may expand and contract according to natural rhythms. Over longer timescales, gradual changes in solar brightness will subtly alter surface temperatures. The sun itself is slowly changing. Over billions of years, it grows brighter as it converts hydrogen into helium within its core. This gradual increase in luminosity will eventually influence Earth's climate more significantly than any short-term variation. Erosion will continue shaping landscapes. Mountains rising today will one day be worn down. River systems will alter their courses. Coastlines will advance and retreat with changing sea levels. Life will adapt alongside these changes. Species will evolve in response to shifting environments. Some may disappear, others will emerge. Just as life has transformed through past eras, it will continue to respond to future conditions. Even the magnetic field may shift again. Reversals will occur over long intervals, recorded in new layers of cooling lava. The geodynamo deep within the core will persist as long as molten metal continues to circulate. On a timescale of billions of years, Earth itself will change profoundly. As the sun becomes more luminous, oceans may gradually evaporate. Plate tectonics could slow if internal heat diminishes.
the planet's surface may transform in ways difficult to imagine today. Yet for now, Earth remains vibrant. It spins steadily, orbits faithfully, and sustains diverse ecosystems. Its internal heat flows outward, its atmosphere circulates, its oceans breathe. Tonight, as you rest, the planet is quietly writing its next chapter. Not with sudden strokes, but with patient adjustments that unfold across millennia. The same forces that shaped ancient mountains and oceans continue to operate, and within this ongoing motion, Earth's future is being formed, slowly and steadily, as it has always been.
If you were to pause time and step back far enough, Earth would appear as a single, seamless system. Mountains, oceans, forests, deserts, ice, air, and life are not isolated features. They are components of one connected planet, each influencing the others through quiet exchange. Consider a single raindrop. It may begin as vapor rising from the ocean, condense into a cloud, and fall over distant land. It might soak into soil, nourish a plant, flow into a river, and eventually return to the sea. Along the way, it dissolves minerals, carries nutrients, and transfers energy. Or think of a grain of sand. It may start as part of a mountain lifted by tectonic forces. Through erosion, it travels to a coastline, becomes part of a beach, and later sinks into marine sediment. Over time, it may be buried, compressed into rock, uplifted again, and begin a new journey. Even air participates in this interconnected pattern. Wind moves heat from equator to pole. It carries dust from deserts to oceans, delivering nutrients that stimulate microscopic life. It transports moisture across continents, influencing where forests grow and where deserts form. Energy flows continuously. Sunlight warms land and water. Oceans absorb and release heat. Atmosphere circulates energy through storms and wind systems. Heat from Earth's interior rises slowly, driving plate tectonics and volcanic activity. Life integrates into every cycle. Plants draw carbon from the air and anchor soil against erosion. Marine organisms influence ocean chemistry. Microbes decompose organic matter, returning nutrients to the system. Animals migrate, disperse seeds, and shape ecosystems through movement. Even seemingly distant systems are connected. Volcanic eruptions can alter atmospheric composition. Dust storms can fertilize rainforests across oceans. Changes in ocean circulation can shift climate patterns far inland. The planet functions as a network rather than a collection of parts. When glaciers expand, sea levels fall, altering coastlines. When forests grow, atmospheric carbon decreases. When tectonic plates shift, mountains rise and climates adjust. Balance is not static. It is dynamic, maintained through continuous feedback between systems. When one element changes, others respond. Over time, the planet seeks new equilibrium. Humans are part of this system as well. Our actions interact with natural cycles, influencing land, air, and water. Yet we also depend entirely on the same processes that have operated for billions of years. Tonight, beneath quiet skies, the system continues. Water evaporates, winds circulate, roots absorb nutrients, tides rise and fall, magma moves unseen below the crust. The planet does not pause. It maintains its intricate exchanges, connecting the smallest microbe to the deepest trench, the highest cloud to the molten core.
And in that seamless integration, Earth remains a living world in motion, balanced not by stillness, but by constant, gentle change.
And now, after traveling through oceans, mountains, deserts, forests, ice, atmosphere, and even the molten core, we return to where we began, right here, right now. The ground beneath you feels still, solid, permanent, yet you now know it is part of something vast and ongoing. Plates are drifting by inches each year. Rivers are carrying grains of sand toward distant seas. Winds are redistributing heat across continents. Beneath it all, molten iron continues its slow circulation. Earth does not rush. Its changes unfold across timescales far beyond a single lifetime. Mountains rise and erode. Oceans open and close. Climates warm and cool. Species appear and vanish. Through it all, the planet maintains a quiet rhythm. You are part of that rhythm. The air you breathe has traveled through forests, across oceans, and through the lungs of countless organisms before you. The water in your body has fallen as rain many times across centuries. The minerals in your bones were forged in ancient stars long before Earth itself existed. Even now, the planet is carrying you. It spins at a steady pace, turning night into day. It orbits the sun in a predictable path, guiding the cycle of seasons. It moves through the galaxy without sound, without interruption, maintaining conditions that allow life to flourish. The magnetic field shields you invisibly. The atmosphere cushions you gently. The oceans regulate temperature quietly. The crust supports forests, cities, and mountains alike. Nothing is static, but nothing is chaotic either. There is structure within motion, balance within change, stability within transformation. Earth's systems are patient. When ice advances, it eventually retreats. When mountains rise, erosion begins. When ecosystems shift, new forms adapt. The Earth is not fragile in the way we often imagine. It is resilient, shaped by billions of years of adjustment. And yet, it is also delicate. Its atmosphere is thin. Its balance depends on intricate feedbacks between rock, water, air, and life. Small shifts can ripple outward through interconnected systems. Tonight, as you rest, Earth continues its quiet work. Clouds are forming over distant oceans. Tides are responding to the moon. Seismic waves from small tremors are passing unnoticed beneath forests and plains. The Earth does not need to announce its motion. It simply continues, slowly, steadily, relentlessly. You began this journey imagining solid ground beneath you. Now you understand that ground is part of a living, moving world, layered, dynamic, and endlessly evolving. So take one more slow breath. Feel the stillness around you. And remember, even in silence, Earth is always in motion.